Run the same program with the same input 1,000 times. You get the same output every time. Most real software fails that test constantly, and most developers never notice. Deterministic code means identical inputs always produce identical outputs, every run on every machine forever. Non-deterministic code means the output can quietly change between runs even though nothing in your source files did. That is the difference between a bug you can reproduce and a bug that only happens in production at 3 in the morning and never again when you try to recreate it. Today we open up the actual mechanisms that make code non-deterministic. Floating point arithmetic, hash map ordering, threads racing each other, hidden inputs like the clock and random generators, the outside world, and uninitialized memory. By the end, you will know exactly where determinism breaks down. Let's start with the definition because deterministic gets used loosely. A deterministic function maps every input to exactly one output with no other factors involved, same arguments in, same result out, full stop. A pure mathematical function like squaring a number is automatically deterministic. But real programs read files, check the clock, talk to other machines, and run on shared hardware. Every one of those is a side channel where extra information leaks into your computation without ever appearing in your function signature. The technical term is a hidden input, not listed as a parameter, but it still affects the result. The art of writing deterministic code is finding and eliminating these hidden inputs, or isolating them when you cannot. Every gotcha in this video is really just one more flavor of hidden input. Floating point numbers look deterministic. They are not in subtle ways. IEEE 754 guarantees that a single operation like adding two numbers gives a precisely defined reproducible result. The trap is associativity. In real number math, a plus b plus c equals a plus c plus b. In floating point, that is false. Rounding happens at every step, and the order of operations changes which numbers get rounded when. A compiler that reorders your additions for speed or a parallel reduction summing partial results in a different order across runs can produce a result that differs in the last few bits. Multiply that across millions of operations in a simulation or a neural network and the drift becomes visible, which is why training the same model twice on different hardware can converge to different weights even with a fixed seed. Hash maps are the classic gotcha every developer eventually trips over. A hash map, dictionary, or set stores keys based on a hash function, and that function does not promise to preserve insertion order. In several languages, iterating over the same keys can produce a different order each program restart, because the hash seed itself is randomized for security, specifically to stop denial-of-service attacks that exploit predictable hashing. Code that loops over a dictionary to build a report or a configuration string can silently produce a different byte-for-byte output every run, even with identical data. The fix is almost always the same. Never depend on iteration order unless the data structure explicitly documents that it preserves one. Sort the keys yourself before anything observable happens and the non-determinism disappears completely. Concurrency introduces non-determinism at the hardware level, and no amount of careful coding eliminates it entirely. When two threads touch shared memory, the operating system's scheduler decides which instruction runs first, and that decision depends on factors completely outside your program, other processes, interrupt timing, even thermal throttling. A race condition is exactly this, a result that depends on which thread wins a timing window that varies from run to run. That is why concurrency bugs are notoriously hard to reproduce. A bug might appear once in 10,000 runs, then suddenly every single time because the scheduling pattern shifted. Locks and atomic operations do not make execution order deterministic. What they guarantee is that whatever order happens, the final shared state stays correct, a different, more achievable goal than determinism itself. Some of the most common hidden inputs are ones you call on purpose. The system clock and random generators are deterministic in the narrow sense that calling them produces a real, well-defined value, but that value is different every time by design. The danger is when these calls get buried deep inside business logic instead of passed in explicitly. A function that silently calls now or random 3 layers deep cannot be tested reliably, replayed from a log, or debugged by rerunning it. The fix used throughout reliable systems is dependency injection. Pass the clock and the random source in as explicit parameters, seeded once at the top of the program. In testing, you inject a fixed clock and a fixed seed, and the exact same non-deterministic by nature function produces identical, comparable results every run. Your program does not run in isolation, and that is another major category of non-determinism, the outside world, reading files from a directory in whatever order the file system returns them, which is not guaranteed to be consistent across operating systems. Making a network call to a service that responds with different latency, or times out, or returns slightly different data because it changed between 2 test runs. Even environment variables can differ silently between your laptop, your CI server, and production. None of this is a bug in the traditional sense, it is real variation in the environment your code executes in. The discipline here is containment. Treat every external read as an explicit, injected dependency, and never let your core logic assume the outside world will hand back the same thing twice. The last category lives at the hardware level: uninitialized memory and pointer addresses. In languages with manual memory management, reading a variable before it is set does not give you 0, it gives you whatever bit pattern was already sitting in that memory location, left over from whatever ran there before. Print a raw pointer address and you get a different number nearly every run, because modern operating systems deliberately randomize where programs load in memory as a security defense, called address space layout randomization. This is precisely why memory bugs are some of the hardest to reproduce. The exact same buggy code can crash on one run and silently succeed on the next. Memory sanitizers exist specifically to make this category deterministic again, by forcing predictable, poison values into uninitialized memory so the bug shows up reliably instead of by chance. So why does any of this actually matter day to day? Reproducible builds mean two people compiling the same source get byte-for-byte identical binaries, which matters for supply chain security. It lets anyone verify the binary you're running matches the public source. Deterministic test suites mean a failing test stays failing until you fix it, instead of randomly passing on retry and hiding a real bug. Machine learning teams chase determinism, so a model trained twice with the same data and seed produces the same weights, essential for debugging and auditing what it learned. Distributed systems like databases and consensus protocols build entire architectures around forcing determinism into a fundamentally non-deterministic network, because without it, replicas would silently disagree. The next flaky test you see is almost certainly one of these 6 causes wearing a different costume. Thanks for watching.